Hello again. It's Thursday. Let's continue our discussion on carbonyl chemistry. So this is the board we talked about what carbonyl compounds are. What do you have to have on the two different sides to basically create 7 different types of functional groups, aldehydes, ketones, and then you have carbon or hydrogen on one side and groups on the other side that renders them to be that makes them uh, to qualify as a living group. They can be they can be kicked out from the carbonyl one of the carbonyl ends. Okay, so they undergo different types of reactions depending upon what you have on the two sides of the carbonyl. If you do not have a living group, they undergo nucleophilic acyl addition reactions because you cannot kick anything out. If you have a good living group, then you regenerate the carbonyl double bond and kick out the living group and replace it with the nucleophile, incoming nucleophile. So that's a substitution. So nucleophilic acyl addition or nucleophilic acyl substitution reactions. Okay. So hopefully you have looked at the pictures and you have also watched the video of the first carbonyl compound. Okay, I'm going to erase the board. I just wanted to show you the board that we had before. Carbonyl, hydrogen, carbon, halogen, nitrogen, oxygen. Depending upon what you have, you make different groups. One hydrogen, at least one hydrogen, that's an aldehyde. That's an aldehyde. Ketone, 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 acid halide, best living group, acid anhydride, very good living group, excellent living group, this whole thing on one side. Okay living group, OH minus or OH2, depending upon how you run the reaction. Acid catalyzed or not acid catalyzed under basic conditions. This is going to be a methoxy or alkoxy group as a living group. If you run it under acidic conditions, then it's going to come out as an alcohol. Works, but then not as great living group as the other two. Amides are chosen by nature quite often. They are living groups, but they're the worst of the bunch. Okay. There are 3 kinds of amides: primary, secondary, and tertiary. This is the connection between the amino acids in a peptide, small chains or long proteins. Okay. The discussion that we are having right now since yesterday is we are having this discussion because of our need to understand the fundamentals of some of our medicinal chemistry topics. All right, I'm going to erase the board. The vertical purple wiggly line kind of, my board is getting trouble. There you go. This detachable eraser. Okay, that goes in the trash. Don't know if this is going to work. We'll try. It kind of works. This is really good workout for me. That's all the matrix can do. I need a new board. I'll probably have to write a new grant to get a new board. Okay, that actually works. That was a lot of work. All right, so let's remind you about the basic chemistry that happens here. Okay, carbonyl, Two lone pairs in the oxygen. Okay, sp2. On this side, you have H or C. On the other side, you have H or C, or you have X or N or O. When you have X or N or O, they constitute living group. When you have H or C, they're not living groups. Okay? Then what happens is a nucleophile can come and attack the carbonyl, goes up, produces the tetrahedral intermediate. Okay, 3 lone pairs, 1 extra, that makes the oxygen having an extra electron, therefore it becomes negative. Okay. H or C, and on the right side you have hydrogen or carbon, or you have halogen or nitrogen or oxygen. Okay, and the nucleophile is stuck here, and this is called the tetrahedral intermediate. Two things can happen. It can either regenerate, that can happen, producing a brand new carbonyl compound, HC, and the nucleophile. This is substitution. And this is, let's use a different color. Let's use purple. And this is, let's save some space. H plus and water, it grabs the proton and it produces a different brand new functional group. Everything stays. Nothing gets kicked out. Okay. NXO on the left side. Oops, wrong. Yeah. In this case, it has to be, see, it's easy to make a mistake. On the right-hand side, it has to be HRC, not NX and O, because they're living groups. Cannot have a living group. All right, the nucleophile is in, and it's picked up a proton from here. See, make an alcohol. So this is substitution, and this is addition. All I want to accomplish right now is give you an idea about what the nucleophiles look like. Okay, so let's draw a list of nucleophiles. I'm not going to be teaching you guys carbonyl chemistry. We're just going to touch on stuff that's relevant to our talks, upcoming talks, our topics, and what you need to learn and what you need to deliver. Because if you are learning medicinal chemistry, and if you do not know how an amide bond happens, or how a protein, we are talking about proteins, so we're talking about receptors, we are talking about enzymes, blocking them, enhancing their activity, reducing their activity, making more protein, making less protein by messing with the mechanisms. But if you're clueless about what the structures look like, how the reactions happen, it's going to be a medicinal crime. So let's bring ourselves up to speed. That's the whole idea. If you're already up to speed, you don't have to watch this. If you're not, if you think that you need this, You should probably watch it and make sure that you understand the materials, because I will be testing you in in-class exams, in assignments, and AI and Chat GPT and other resources will not be used. So you're pretty much on your own. Okay. All right. So nucleophiles. Let's discuss nucleophiles. Nucleophiles. We usually write them as uppercase N, small u with a lone pair. That's a nucleophile. Okay. And so anything that has lone pairs may constitute as a nucleophile. It's also a relative term. Like being an acid or being a base is also relative. Water can be an acid at sometimes, at some moments. It can also act like a base, depending upon who else is around. Okay. So the easiest and the most available species that can act like a nucleophile is water, because it has two lone pairs. This is a neutral nucleophile. If you want to produce the same product, if you want to add an OH to wherever you are trying to do the reaction at, but if you want to have a stronger nucleophile, then you need a species where the hydrogen, one of the two hydrogens has been knocked out, okay? And you have formed a hydroxide, such as this. OH minus. OH minus cannot come alone. It has to come with a cation. So this is going to be sodium hydroxide, packaged as sodium hydroxide, potassium hydroxide, calcium hydroxide, etc., etc. So this is a nucleophile. That's a nucleophile. That's an anion. It can also work like a base. The difference between a nucleophile and a base is the following. Nucleophiles can attack a carbon, electrophilic carbon. Base is a base, which may look like a nucleophile, but base is when that species is grabbing a proton. Okay, when it's plucking a proton to neutralize itself. If the OH minus is plucking a proton, then it's not a nucleophile, it's working like a base. Okay, keep that distinction in your hard drive, in your accessible to your RAM. Okay. Nucleophile, neutral nucleophile. You can also have ROH. So these are alcohols. They are nucleophile. They're very similar to water. One hydrogen has been replaced with an R, and that's an alkyl group. An example will be methanol. Okay. Your favorite alcohol, ethanol. These are examples. That's an nucleophile. You can also play the same trick. You can pull out that proton on the alcohol using a strong base like sodium hydride, calcium hydride, sodium metal, things like that. And you can make RO minus and a cation, whatever the cation is. Let's say sodium cation, Na plus, and that's a more awesome nucleophile that can also backfire on you, that can pluck a proton and neutralize itself. So you have to be careful how you use it. These guys are called alkoxides. Okay? Not alcohol, alkoxide. What about nitrogens containing species? Well, they are nucleophiles too. Ammonia is a nucleophile. Between ammonia and water, which one is a stronger nucleophile? Ammonia is the answer. Think about it why. You learned it in 128A or 128B. I usually talk about it. Ammonia is a great nucleophile. If you replace one of the hydrogens with an R group, then it's an amine. then it's a primary amine. It's a great nucleophile. If you replace two of the hydrogens with an R1, R2, R1 and R2 can be the same species. They can both be a methyl. They can both be ethyl. They can both be even aromatic ring, right? Same is true here. Well, same is not true here. If it is aromatic, then things can be a little sketchy. Aromatic alcohols like phenol, they're like quite different than aliphatic. So there is a slight difference between the two. I'm not going to get into the details right now, because then we will never finish our discussion. Oops, sorry. Nothing. So when you have only one hydrogen attached to the nitrogen, that species is called a secondary amine. Okay. Tertiary amines are not nucleophiles. Why? Because they do not have a hydrogen. These hydrogens play a very significant role for it to work like a nucleophile, because they are coming in as a neutral nucleophile. At the end of the day, after their attack, they need to lose a hydrogen from either the oxygen center, which is the nucleophilic center, or the nitrogen center that attacks with the lone pair. They need to have a hydrogen that they can lose to utilize that bond between N and H or O and H. That bond becomes their missing lone pair so that they can become neutral again. If you're completely lost right now, we can discuss it not during more class, but some other time. If you are confused about it, I'll be more than happy to go over it. I'm not going to talk about it right now. So tertiary amines, where you don't have the hydrogen, it's R1, R2, R3, like triethylamine. We use it all the time in our lab in reactions as a base, as a proton scavenger. It picks up proton. That's what it can do. It can never work like a nucleophile. It tries to, but it doesn't produce any neutral product. Okay, I'll pause. Nucleophile, 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 awesome nucleophile. Can you have a hydrogen nucleophile like a hydride? Yes, you can. Very unstable, and they usually come in a special package. I'm just going to use two examples, the two examples that we use in 128A and 128B. I'm going to put a parenthesis, and I'll say sodium borohydride or lithium aluminum hydride. They carry H minus hydride, kind of disguised, masked H minus. So when you dump sodium borohydride in your reaction mixture, it provides the reaction with H minus. Okay, so that's a hydrogen nucleophile. Can you have an alkyl nucleophile, like a carbon nucleophile? Absolutely. Grignard reagents. Okay, Grignard reagents are RMgX. Mg is magnesium, X is a halogen. Most of the times it's bromine. And this R can be either alkyl or aryl. Aryl means aromatic. So it can be CH3, it can be CH3CH2, it can be phenyl, it can be whatever. Anything. Those are kind of like R minus. It's not R minus. The carbon magnesium bond is extremely polar covalent bond. Very, very polar covalent bond. And carbon being more electronegative than magnesium, that bond is pulled toward carbon, making the carbon the nucleophilic center. I'll just draw one more carbon nucleophile. It's kind of my favorite. R, triple bond carbon with a negative charge and a sodium or potassium. This is also a nucleophile that you can pretty easily generate. The terminal alkynes, when you have a hydrogen, the pK of the terminal hydrogen is like 25. You can pull it with a strong base and make a triple bonded, I think it's called alkylidine or something aniline. Alkynyl or something like that. I'm not 100% sure about the last letters, 2 letters, okay? So these are different nucleophiles, okay? I think you should print it out and save it, or you should just save it somewhere so that you can refer back to it. I'm not sure if the textbooks actually use this way of formatting the presentations. What I'm going to do is I'm going to take a snapshot to add as a still picture with higher resolution, because sometimes the videos are very pathetic with their resolution. Let me take a picture, okay? I'm going to block the camera for a second. Okay. All right. With that, I'm going to quickly switch to amide. How do you make an amide? And the old-fashioned way and the not old-fashioned way, okay? There are amide chemistry synthesis has been bitten to very thin sheets over the past years, over the past decades, okay? Because people are interested in peptides, people are interested in making proteins, people are interested in making like natural compounds, people are interested in making drug candidates. I told you that there are some problems with peptides, so other peptide-like molecules have emerged over the years in the past many decades. They're called peptoids, which are like peptides, but not exactly peptides. You mess with the amino acid, make it look like an amino acid, but not an amino acid, to fool nature so that they don't get kicked out from the body too fast. They don't get catabolized or metabolized too fast. They last longer in the living system, in the bloodstream. Okay, they don't get produce metabolites and get out of the system through urine or feces too fast. Okay, in that case, you cannot really. It's not drug-like. All right. What I'm going to do is I'm going to keep this as long as I can save them, the pictures of the nucleophiles. But let's quickly switch to the amide chemistry. My board needs to be replaced. I don't think anybody is going to give me a new board if I make noise about it. But this is actually good workout for me. All right. Amides. Amides are important. And we're also going to talk a little bit about amino acids. How long has the video been going on? I don't know if it shows anywhere here. It says recording, probably 15 minutes, 20 minutes, something like that. Okay. So I'm going to give you a generic idea about how to make amides. Okay. Before we do that, I'm going to draw a hill, and I'm going to show you the 5 different carbonyl compounds with a leaving group on the hill. If I draw the hill and place them at different parts of the molecule of the hill, I think it'll make more sense to you guys. Maybe it'll stick better to your memory. Okay, so 5 compounds: acid halides, anhydrides, carboxylic acids, esters, and amides. Those are the 5 carbonyl compounds spread over the hill: Huntington Lake, Shaver Lake, Aubrey Valley, 2 compounds, and the foothills where civilization begins. Sorry, don't take it personally. Don't get upset. I mean, I don't know what I should say or not say to not upset anyone. If you get upset, come and talk to me if I'm hurting anyone's feelings accidentally. All right, so on the top of the hill, it's going to be, I'm going to stick, just like in the past, I'm going to just stick a methyl group on the left side, okay? It doesn't have to be a methyl group. It can be a hydrogen. It can be an ethyl. It can be a long chain. It can be a cyclic compound. It can be an aromatic compound, benzene ring or some other thing. So keep that in mind. Methyl, I'm just picking methyl because it's easy to draw, just a stick. Okay, on the right side, it's going to be a chlorine. Okay, it's an acid halide. We already talked about. This is on top of the hill, most reactive. Down the hill, it's going to be an anhydride. This is an anhydride. Two carboxylic acids condensed, loses a molecule of water, and they get joined. Okay. Let's write their names all in black. Acid halide and hydride. Down here, carboxylic acid, Aubery, Huntington, Shaver, Aubery. Same height, energy-wise, because their reactivities are same. Carboxylic acids and esters. They're very similar reactivity. And no hydrogen, a methyl group. This is what I had used as an example yesterday. And at the very end, the most unreactive species happens to be an amide. And I'm just going to make it like a simple amide, maybe a secondary amide, because that is more relevant to the amino acid situation. Okay, I'll keep one hydrogen and one methyl because this is going to be similar to amino acid coupling with another amino acid. Okay. So acid halide and hydride, I'm just going to call it acid, carboxylic acid, ester, and amide. If I ask you what kind of amide it is, secondary amide. Whatever I'm teaching you guys, even on using the videos, I'm going an extra length. I expect you to learn it. Whatever I'm covering in the class, whatever I'm covering in the videos, I expect you to know the material because you will be tested on. So don't take it too lightly if you want to get an A in this course. You have to earn it. Okay. Most reactive, pretty reactive, not so reactive, but that can work, not reactive at all. Okay. Now let's look at the leaving groups. What are the leaving groups when they get kicked out? Okay. The leaving group here is going to be Cl minus. Cl minus is an awesome leaving group. Why? 128A and B. We can discuss it later if you want. Pick my brain, talk to me, have some brainstorming session. We can discuss it, not in the classroom, not here, but do not feel bad to ask me. I will be super happy if you ask me, like, can we go over some additional stuff? That's why I have office hours. That's why I do not have to have office hours on the specific times. You can just let me know when you are available. As I said, if you come in a group of 2, 3, 4, 5, 6, 7, 8 people, that'll be more welcome. Okay, if you bring some friends from the 240T class. Cl minus is going to be the leaving group here. The leaving group here is going to be this. It's a weird leaving group. This is very stable. Leaving group wise, great. Leaving group. This guy is very stable. Stable means great leaving group. Unstable means bad leaving group. This is also a great leaving group. It's also very stable because the negative charge is spread around. The negative charge can spread by doing resonance. It's not a secret. The leaving group here is going to be OH minus. Okay. Leaving group, not that stable. In this case, the leaving group is going to be methyl and an oxygen. Not so good. Okay. Leaving group, not so stable. This dude sucks. It's terrible. H, it already has a lone pair. And the methyl group is not going anywhere. And it gets a second, because this is where you cut the molecule. When the leaving group leaves, this is where you cut it. This is where you cut the bond. Where is it? Here. Okay, so the electrons here and here go with the chlorine. Electrons here and here go with the oxygen. Electrons here and here go with the oxygen. Electrons here and here go with the oxygen. Electrons here and here become the nitrogen's second lone pair. Different color, but then don't get too bogged down with the colors. Negatively charged. This is a terrible leaving group. Okay, makes sense? That's why this is the most unstable leaving group, most stable leaving group, pretty darn good stable leaving group. So. That means this is most stable, least stable, very unstable. Okay. So making an amide from the top of the hill, going downhill is possible, going uphill is painful. Okay, there are tricks that we play, but then going downhill is much easier. So how do you make an amide? Okay, so this is your target. Since we're going to be talking about some peptides and proteins and amino acids, I think we will focus on how to make an amide. Okay, this is going to be your target. So let's use a color that's kind of prominent. This is your target. Okay, you want to make that, right? You want to make this. Do you want to start from here? Do you want to start from an anhydride? Do you want to start from an ester? Do you want to start from an acid? Well, the chemistry has been improved quite a bit over the past many decades for making an amide bond. It's almost like people make fun of people, scientists who have only spent time making amide bonds. We had gotten into some trouble, interviewing with like big pharma companies because they would look down upon us in our research group in Irvine, and that caused a lot of problems because our entire group was pretty upset. So that happens. So people have biases and they stereotype, things like that. So if you're just focusing on making amide bonds, it's actually the chemistry has been figured out pretty well. So the challenges are less. So despite the fact that we got upset, not so much so with as far as I'm concerned, but my colleagues were pretty upset, our boss was pretty upset, but then making an amide bond is actually not that difficult. It's pretty straightforward. Okay. So you can make it from here. A lot of times you start from the acid. All the amino acids that you buy from companies, okay, they come as a free acid, then you react them with fancy reagents that can render a carboxylic acid for the reaction to make an amide. The reason I'm having this discussion is because you cannot directly make an amide from an acid, carboxylic acid, using standard protocols. I'll explain why. Okay. So generally, this is your target, right? Many compounds, many drug-like compounds, many proteins, peptides, they have amide bonds. So this is where you want to go. You usually start from here. The starting point is the carboxylic acid. Carboxylic acids are pretty robust compounds. They're not very unstable. They're not as reactive as acid halides or anhydrides. They don't go bad. In Fresno, the moisture content is less, humidity is less. So those guys are more stable. But if you take an acid chloride and if you don't close the bottle very carefully in a highly humid place like, I don't know, the East Coast, southern part of the country or in India, it'll probably decompose to the carboxylic acid. So you don't usually buy an acid chloride or an anhydride. You can, but then generally you keep your starting compound as an acid. Okay, so you start from the acid, and then there are tricks to go uphill. Okay, you start at the Aubrey Valley, and then you climb up here using a reagent called thionyl chloride. SOCl2 and heat. 128B material. I'm not going to go over that. If you want to know, how to you go up there because you have to kind of push yourself up on the high elevation at Shaver or Huntington. Then you can roll down all the way to the valley. Okay, you go up there, or you go up here doing some chemistry with phosphorus pentoxide. There are fancier ways. This is very traditional and classic methodology. Thionyl chloride and P2O5. P2O5 is terrible. It's a very caustic and terrible compound, but you can do it. In the old days, you can do it. This is what we teach in undergraduate chemistry. So I'm using it, hoping that it'll bring back memories from the past for you guys. Then from there, you can roll down to the amide, easy breezy. Okay, it's very easy. So you go from here to here. What you use? Well, what are you replacing and what are you replacing with what? You're replacing this guy. Think about it like this. If I can use like a little model here. If this is a model, this is a makeshift model of the acid halide. Think about it. It can suffice as a model. This is the carbonyl. That's the methyl group, and that's the chlorine. That's going to get kicked out. And you're entering. Let's say this guy is the whatever the N with the hydrogen and methyl. Okay, think about it that way. Let's say that this is your incoming group and that's your outgoing group. All you have to do is bring in the incoming group so that it can come, attack the carbonyl carbon, push the double bond on top of the oxygen. Oxygen that kicks back, then it gets stuck here. Okay, You get the tetrahedral intermediate. It's going to have a tetrahedral shape. I wish I had more dexterity. You get the tetrahedral intermediate, that's O minus. O minus kicks back, becomes carbon double bonded oxygen, and kicks out the chlorine and becomes planar again. This is the leaving group, Cl minus out, and then you get the brand new amide bond. Can that make sense? I hope it makes sense. So what do you bring in? What's going to be your nucleophile? Well, let's see how much attention are you paying? You are giving to this talk. So the nucleophile is going to look like this. Just copy from there. N H methyl, and you want that guy to be a neutral nucleophile coming in as primary amine. So what do you want? You want a second hydrogen, this guy, in a lone pair. Okay, so you need methylamine. Methylamine will come in, attack, push, kick back, chlorine out, and eventually it'll lose a hydrogen to get its lone pair back. Because remember, at the very beginning, it's going to use its lone pair to make the first bond. This lone pair is going to be its bond between the nitrogen and the carbonyl carbon. That's the lone pair. If I change the color, that's the lone pair. But then it lost the extra hydrogen to bring back its normalcy, like make itself neutral again. Make sense? So this is a standard procedure by which you can make an amide bond. Okay, this is not how peptides are made. Peptides are often made in a peptide synthesizer, like one that Kalyani, Dr. Maitra, other Maitra has in her lab. It's a microwave-assisted peptide synthesizer. Half of the unit was mine. Like when I came here, I bought it, but then I donated to her to save her like $35,000. The whole machine was like twice as that. So in order for her to save some money from her startup funding from our university, I wanted to donate that. And I think now we are beginning a collaborative project. The machine is down for the time being. Machines, instruments are great when they work. When they don't work, you have to fix it. Okay, so you can go from the acid halide to the amide, or you can also go, I don't know how am I going to draw the line. You can also go from the anhydride to the amide. What do you use? Same thing. You use the same amine, methylamine, 2 hydrogens. Okay. This is what you use to go from here to here or here to here. Make sense? So this is how an amide bond is formed. There are fancier ways to make an amide bond, starting directly from the carboxylic acid, but let's not talk about that right now. Let's take a picture. I think I've been talking for almost 45 minutes. Let's take a picture and maybe we'll just call it a day. For the time being, I have to take care of a couple of other things. I want to make a video on amino acids. Maybe when we talk about amino acids, we will talk about the fancy way of making amide bond, how amino acids are connected together to make a peptide. Okay, I'm going to call it a day for the time being. This will be video number 2, and I'll add the still pictures to the list. But then I will probably get back to making one more video before our class today on amino acids and how amino acids are connected, coupled with each other using much fancier, a little more expensive, but affordable ways, starting directly from carboxylic acids. And I'll also talk about what will go wrong if you try to use a carboxylic acid and an amine to make an amino acid, or to make an amine bond. You might be wondering, like, this is up on the hill, so why can't we just take the acid and react it with an amine, excuse me, to get the final product? This is a better living group. This is a better living group than that. They should work. They should work, but something goes wrong. It's one of my favorite questions. Sorry, it's one of my favorite questions in 128B. We'll talk about that in the third video. Hopefully, I'll get to the third video today. Let me just wrap this one up, make a YouTube link, and then I'll post it on Canvas.